Dominik Laux. I'm working in the product development department at Aurora Tech. And FireAid is a project that we just recently got funding for. But it's very fresh, so it's very in the beginning. It just started this summer, so it's more like of a preview. But I will start with a general overview on Aurora Tech, what we are doing as a company, on our like wildfire solution, which is like the web app that we are developing, how we use fire currently for fire spread modeling, and about our satellites. So yeah, this is like Aurora Tech. So we are, this is our thermal infrared imager. So we are building satellites, like CubeSats. So this is the payload that we are developing, and we are launching them within like a constellation. So basically just like a bunch of satellites focused on wildfire detection, especially on early detection and monitoring. So by launching these constellations, we actually just increased the overpass frequency to increase the temporal resolution. We do on-orbit processing to reduce the latency between hotspot detection, like the acquisition of the image and the detection on ground. And we not only gather all this data, but we also want to actually provide insights to users. So we are working on this like end-user platform, which is like called Wildfire Solution, as I said. We were founded in 2018. We've been growing quite a lot in the last years, also collected quite some users. Yeah, I mean, like we are integrating these available satellite sources and launching our own satellites. And I mean, yeah, so we like funded by investors, but probably worth mentioning is that we recently closed 2 large contracts. So there's like a contract with Greece, like the Greek Space Agency, to build up a satellite-based wildfire detection system, and also the same thing with the Canadian Space Agency. Like we are building the satellite constellation for WildfireSat together with Spire, which is like the platform provider for the satellite. Regarding like our wildfire solution, the core of this is actually the product that we call aggregated active fire. So basically this is just an aggregation of basically all available satellites that are suitable for wildfire detection. So we are really focused on completeness. So we do spatio-temporal clustering for all these different sources. We are putting a lot of effort in reducing the latency by using direct downlink and direct broadcast wherever possible. And we also like trying to add all this contextual data into the service. So this is like the fire season in Quebec from 2023. And here is like the visualization of all the satellites that we are integrating. So this is the list of LEO satellites. I mean, it's like the NASA satellites, the Sentinels, also like a Japanese satellite, and Fengyun 3E, like the Chinese satellite. Forest 2 is like the first commercial satellite of Aurora Tech, and this is the first plane. This is how we call it. So it's like the first orbital plane of 8 satellites that we launched in May this year, which is still in the commissioning phase. Yeah, by that we just want to increase this number of daily scans that are available to monitor wildfires. And as mentioned, we are leveraging direct broadcast wherever possible. So this is basically means that you can receive the raw data before it gets processed, and then just do the processing ourselves to get the detections. So yeah, this is how this looks then actually in the web app. So this is like the global view that you would get if you enter the platform. And usually, so you have these red icons for fires, black icons for static heat sources like gas flares or industry sites. And then what you would usually do as a user is like you can create a monitored area, and within this monitored area you will get notifications. So at the moment that we receive any new activity, like a new hotspot detection, you will get notified by like email or WhatsApp, and to get an overview of the current situation. So if you would then like zoom in to the incident, this is what you see. So basically, you get these hotspot detections, and they are like we do this spatial temporal clustering, and you get a bunch of information. So the first hotspot, the last hotspot, the lifetime. Then there are a couple of measures to filter out false positives. So we have this fire confidence metric that assigns like a confidence value based on a couple of factors. So based on the FRP, the like maximum normalized FRP, also the geopersistence, which is like the number of consecutive geodetections, then the number of different satellites that detected this individual cluster, and also the combination of algorithms and satellites to get like, confidence value of how, is this actually a fire or is it just a false positive? Here you can see like all the satellites that are integrated. You can also view the shape based on individual satellites. And there is like what I said, like a bunch of contextual information. So you can have actually there's a tool to classify fires, to also attach a status to it. So if it's already like detached or if it's closed. And then you can also see like a list of upcoming LEO satellite passes. This one. You just like get like a prediction of when the next satellite overpasses, or when you can expect new data. Then you can play with this time slider. So this is like an historical event in USA. It's the Madre fire. So if you then just change the time slider, then you will get like the next state of the fire. In blue, you can see the hotspot distribution. And then you can see how the fire evolves. Like, and the red indicates like the detection time. So you can see like red hotspots that are newer and older hotspots that are like more brownish. And yeah, this is just one example of the contextual information. So this is then the land cover overlay that you can activate and, for example, see the distribution of the different land cover types within this cluster shape. Yeah, actually, I wanted to show like how this would look like for a current active fire. So just trying to do a quick live demo. So this is like the current view on Europe for the last 2 days. So this is the current situation. You can see a bunch of static heat sources, but there's, for example, this active fire in Spain. Then, for example, you could switch to the satellite base map. And then, as I said, so you get this information, then you basically can just check. So this was initially detected the day before yesterday in the evening. So you can basically check the first hotspots. So this were VIRS hotspots. And then quickly after that, you also got the MTG, so Meteosat 12 hotspots, which are included in the notification, but not in the clustering. So they are not included in the shape because of the coarse ground sampling distance. So they're not included in the actual cluster shape, but still used like to get a complete picture of the fire. And then, I mean, you can see that there's like a large gap. Then there are new detections from today in the morning. And this is how you then get like a picture of this fire. And like this gap directly leads me to why we are actually developing our own satellites. So this is a graph that shows like the local time and the overpass times of satellites typically used for wildfire detection. So in gray, you can see other LEO satellites, and in like the colored ones are our own satellites. So what you see is there's like this distribution of fires. So usually there's this peak burn period where fires reach their highest intensity. And this is exactly the time where there are no satellite overpasses. So we actually have like a gap where you don't have any information about the current state of a fire because they will have overpasses afterwards or before. And this is actually what we are targeting. So we want to launch satellites that actually bridge this gap or cover this gap by additional overpasses. So this is like a visualization of that. So you can see the orbits of the satellites currently used for wildfire detection. And then the red box visualizes this lack of overpasses in the late afternoon, where it would be most crucial. This is the timeline. So we launched like a first prototype in 2022. Then the first commercial satellite, which is called Forest 2 in 24. Forest 3 is another satellite where we actually also built the platform ourselves. And then, like as I said, in May this year, we launched the first plane of 8 satellites, which we call OTCP-1. So these are currently in commissioning phase, and we are expecting data to be available by the end of the year. Then there is HFS, so Hellenic Pharisat, which is the Greek constellation, which will be also launched end of this year or early 26. And like the long-term vision is actually to have like a full constellation of 100 satellites visualized on the right to really reach this 30-minute revisit frequency. Some specs on the satellite. So this is like an image. So it's really just like a shoebox. This is the size of the satellite. So it's not comparable to the traditional satellite missions that like cost millions of dollars. So it's really just like this shoebox size satellite. And this is the infrared imager. It has a 400 kilometer swath. The ground sampling distance is 200 meters. And we have like this medium wave infrared channel for wildfire detection and 2 long wave channels where we're currently investigating to use this also for LST, like a land surface temperature product. And the data from our own satellites is actually what is the core of what we call near real-time active fire. So this is really like the high resolution, low latency product. And these are detections from Forest 2, so the first commercial satellite, where you can also compare this to VIIRS, like where you get like a picture of how the high resolution helps to actually get an accurate representation of the current perimeter. The same is true for this picture. It's again like a comparison of the Forest 2 detections against VIIRS detections. And one thing that we also focus on is on-orbit processing. So to reduce the latency, we don't downlink the whole raw data because this just takes long. So we are working on our on-orbit processing algorithms, also AI-based, to actually detect fires in space and then just downlink the locations to reduce this latency, and then also using like a direct downlink to get the data as fast as possible. Yes, that's that. And so this was about the satellites. So now back to the end user platform. So it's not only about the monitoring part, which I just showed you. So it's also about supporting this whole wildfire management decision operational chain. So it's about supporting decision making. And one step into that direction is actually has been the integration of ForFire into the platform. To also like get it like the situational overview and get a first quick estimate of where the fire potentially will spread. So this is like the ForFire implementation. So basically we just built up on the ForFire solver and focused on a user-friendly interface with the idea that you would really just like you would get a new detection in the platform. You will get a notification, then you can just directly run a first quick estimate by just having to click on one button, and then you will get like a first estimate on how the fire potentially spreads. So this is like the whole idea. So we focused on usability, so you actually don't have to fetch data, you don't have to change between platforms. The data is just fetched automatically, but you can also customize the inputs, so you still have the option to change this. This is how it would look like in the platform. So this is like a random example from last year in the US. So you would, as I said, you get this initial detection, then without having to switch platforms, you would just run the ForFire solver on this. Input data is fetched automatically. Let me quickly go back. So it's fetched automatically, but you can also choose between different weather models. So we are using this open weather API that usually provides like a best match option, which just chooses the model with the highest spatial resolution in that region, but you can also select explicitly, so for example, the HER for the US, or like European models in Europe. You have a couple customizations options, as I said, and then you can just run it. And as this is like a historic event, you can also compare, this is the fire line intensity, and then you can also compare the prediction to the detected cluster shape that was detected afterwards. Yeah, that's that. And so this is actually like, I mean, fire spread is in high demand, so we got like quite good feedback for it. I mean, it's also important to say what it is, so it's like really just this quick estimation. So what's next? And on our side, we are now working on this project to actually develop these like AI-driven decision support tools, which is, as I said, like really just like a sneak peek because we just started this. So the objectives of this project is actually like working on an ML-based fire spread modeling, get some automatic suggestions for fire break placements, and then also like a feature for triage and prioritization of events that happen like simultaneously. And eventually this shall go into the platform. We've been looking a bit into existing data sets, but usually they are really focused on individual regions or limited in terms of their samples. And also we want to focus on sub-daily predictions. So we are currently working on assembling a data set, leveraging like this archive that we have from the platform where we aggregate all this satellite data, which goes back for 5 years. Yeah, we want to like assemble a data set that we can then use to train a model. The idea is to look into graph neural networks for fire spread modeling. So this is something that we want to try. I mean, we might end up using different methods, but this is something that we want to investigate. So there have been recent publications that looked quite promising. So basically, your graph is just like a collection of nodes with dynamically changing input features. And then the edges represents like the fire path with a certain probability and the relationship to the neighboring node. And then for the fire break placement part, we want to look into reinforcement learning to actually train an agent that identifies these critical nodes that can then be used to optimize towards a certain objective function, like reducing burnt area or reducing the distance to roads, to assets. But this is very preliminary. I'm hoping to be able to present some first results soon on this. Yeah, that's it from my side. Thanks for your attention.